So far in this week, we have discussed the utility and philosophy of regression in dealing with experimental data. We have discussed simple linear regression, and also we have discussed multiple linear regression. In simple linear regression, we have one independent variable. In multiple linear regression, we have several independent variables. But both are linear in the sense that the normal equations which will give us the regression coefficients, they are linear equations. But sometimes it may happen that we are trying to fit some function which gives nonlinear normal equations, and that is the kind of regression we will be talking about now. When we say nonlinear equation, we do not mean that this independent variable x and dependent variable y, they are connected nonlinearly. They may be connected nonlinearly, but when they are connected nonlinearly, it may give linear or nonlinear regression problem. As we have seen before, if y hat is w0 plus w1x plus w2x square, if this is how x and y are related, then it becomes a linear regression problem. Multiple linear regression, but it is still a linear regression problem. But there could be other type of relation where the normal equations will become nonlinear, and we will see that kind of regression now. Now, when normal equations become nonlinear, then all the techniques that we have learned so far, they will not work. We have to find something else. The simplest way is to try to convert the relation between y and x in such a manner that the normal equation becomes linear, and that is something we'll see in this lecture. So recall our discussion of linear equation. Here y hat is xtw, where x is the regressor, vector regressor. It has components 1, x1, x2 up to xk, and w is the regression coefficient vector. It has component w0 to wk. So for each experiment I have yi hat is equal to xit multiplied by w. But in general, we can write this y hat is a function of x and w, and that y hat I is a function of xi w. So now the cost function EW is given by 1 by n summation of yi minus yi hat, that means this f xi w whole square. And our goal is to find out that particular vector w which will minimize this function e. To do so, we take this derivative del e del wj and make that to 0 for j going from 0, 1, 2 to up to k. So it will give us w0, w1 up to wk. If I take the derivative, then this 2 comes out. It becomes 2 by n. Whatever the third bracket, it will be there, and then there will come this del f del w j. So I have removed this 2 by n from here. So del e del wj is 0. It gives us this equation, that summation I1 to n, this part in the third bracket yi minus y hat I multiplied by del f del wj. It should be equal to 0 for all these j's. In fact, this del f del wj is the gradient of f, and we can write that way. yi minus y at I multiplied by gradient of f equal to 0. It will give us all the values of w. So these are the normal equations which are solving w. So far so good. We are using this for some time now. The only problem is that so far we were using f to be of this form, and when it is of this form, then this normal equation becomes linear in W. But in nonlinear regression, this f is such that this normal equation will be nonlinear. In that case, the solution becomes complicated. There are of course several techniques that how to deal with such issues. Typical techniques are Gauss, Newton, steepest descent, Levenberg-Mark, etc. But what we will do now is that we will try to modify this y hat in such a manner that it becomes linear in W. So let us see that how we can do so. Let us take an example that we are trying to fit y hat equals W naught x to the power W1 over this data set xi yi I equals 1 to n. My cost function e is now 1 by n summation of yi minus W naught xi W1 whole square. So now if I take for instance del E del W dot equals 0, then taking the derivative of this function, this 2 will come out. That will give me 2n summation of whatever there in the first bracket. And then I have this minus W naught xi W1. I have to take its derivative with respect to W naught, and that will give me xi W1. So this gives us one equation. Another equation will come from del E del W1 equals 0. Once again this 2 will come out. So it will be 2 by n, and then again this minus W naught xi W1. I have to take a derivative of this with respect to W1 now. But W1 is the power of xi. So when we take the derivative, if we take the derivative of a to the power x with respect to x, then it becomes a to the power x ln a. So in that way, here this is xi W1 and natural log of xi. So these are the normal equations. We can solve them and get the value of W naught and W1. But if you take a look at this equation, you will feel that these are nonlinear in W naught and W1. Don't bother so much about xi yi because we know the values of xi yi. W naught and W1 are the unknown here, and it looks like that these equations are nonlinear in W naught and W1. Since this is nonlinear, we have a problem that how we are going to solve it. So first we will try linearizing this fit. We'll modify this one in a way that it becomes linear. So how we'll do so? So let us take this example where x and y are this data set. X is my independent variable 1, 2, 3, 4, 5, and y is the dependent variable or response spanning from 0.4 to 8.4. If I put it here, through these red dots are these data points. Looking at this, it looks like that it may be nonlinear the way the curve is going. So we have assumed that y hat is equal to W naught x W1. Either we have assumed it from the shape, or we have some knowledge of theory from which we argue that it should be of the shape like this, W naught x to the power W1. Now that we are trying to fit this, we are having the problem exactly what we have discussed, that the equation for W naught and W1, they are nonlinear equations. So therefore, we want to transform this by taking log both sides. If I take log, then log of y hat equals log of W naught and W1 log of x. So it tells me that in log of x and log of y, they are actually, it's a linear relation now if I take log of all of this. Therefore, if I take the log, this ln x and ln y, I transform this table to this table. These are the log values of this x and y. And now if I put these points here, all these points are here. If I put it here, ln x versus ln y, this is a linear relationship. So I have my new variables ln x, ln y, and let us say I have this capital W naught and capital W1. These are my regressor. Capital W naught is ln small w naught. So if these are my regressor, then this is a linear relationship now. So I can fit a straight line here and I can get this ln w naught. Capital W1, small w1, they are just the same. So there is no difference. I can get this capital W naught by fitting a straight line here. From that I can get this small w naught because they are connected with capital W naught is log of small w naught. And finally I can fit this y w naught x to the power w1 by transforming this to a linear function. Now it looks quite all right. We can use simple linear regression now, but it's not always as good as it looks. One of the problem of this approach is that usually when we have studied linear regression, we know that we have assumed that y and x are related like this, theta naught plus theta 1x plus some noise epsilon I, and based on that we have limited data. If we have infinite number of data, then we can actually find this theta naught, theta 1. We have limited data. We are trying to fit a least square regression that would be w naught plus w1x. And we hope that y is equal to w naught w1x plus this e. This e will be somewhat close to this epsilon. And this w naught and w1 will be the least square estimate of theta naught and theta 1. So in that sense, when we try to fit a curve like y hat is w naught x to the power w1, the basic assumption here is that this noise here is multiplicative. Because if it is not, if there is an additive noise, we cannot just take the log because there is a plus noise. So this is the shortcoming of linearization procedure, because in many cases noise is not multiplicative. If the noise is multiplicative like this, then it's fine, but in many cases it is not. So that is the problem of linearization, and that is why linearization may not be acceptable all the time. There is another problem. We can have other kinds of model. We are not going to get this kind of model all the time. For example, we have, let us say, this kind of a model. If we have this kind of a model, then this theta naught, theta 1, theta 2, theta 4, linearizing this expression is slightly difficult. So we have to go then for nonlinear regression, use some other techniques. There are usually two approaches. One is that we don't bother about this creating normal equations and then solving the normal equations. We directly minimize the cost function and check that for which value of w the cost function will be minimized. Or we actually deduce the normal equations and then we use techniques that we have described before, such as this Gauss-Newton type technique that we have talked before. We can use them and solve this nonlinear normal equations to get the w vector. So to summarize, here we have seen that how we can transform nonlinear regression problem to linear regression problem. We use this method most of the time But we have to remember that this method may not be very accurate. It may be acceptable in some cases, but not always, because of the nature of noise. For your exercise, you use this dataset that we have just discussed, and using the technique we have just discussed, you fit this y hat w naught x to the power w1. So you linearize this, and then you fit the new values of w naught w1, not w1 really, the w naught will get new value, that log value. From that you can get this old value of w naught. We have only 5 data points here, so you can do a manual calculation. It doesn't require a computer program. So that's all for this lecture. Thank you, and I'll see you in next class.